Hey folks, and welcome to Chapter 7. Today we will be looking at changes of state and the gas laws. The first section here is just about changes of state, or we may call these phase changes. So when we start talking about phase changes, we should first back up a bit and talk about what phases are, right, or states of matter. And this takes us back to the very beginning of the textbook and the very beginning of the semester when we talked about solids, liquids, and gases, right? These are what we mean by phases or states of matter. This slide right here is actually a throwback from chapter 1, where we were looking at what, solid, liquid, and gas really are at the atomic scale, right? So solids, liquids, and gases are like observations that we can make at the macroscopic scale, the human scale. We can see how things behave, but we want to explain these kinds of things by talking about what's happening with the particles or the molecules, the atoms that are involved. And that's what we get to down here, right? So for a solid, the volume and the shape are fixed. The particles themselves are strongly interacting with each other. They are low in kinetic energy, and while they're always moving, vibrating, jiggling around, the relative motion is quite low compared to the other states, like liquid, which has a fixed volume, but of course we all know that it will take the shape of whatever container you put it in. Liquid particles kind of fall over each other a little bit. They're weakly interacting, and they are farther spaced than solid particles, and they have more energy, but still less than gas particles, which are the highest temperature, highest kinetic energy, most motion type of phase, right? The volume is unfixed, the shape is unfixed. They just take whatever container they happen to fall in. Okay, so that's all old stuff that you know, right? Now we're going to be talking about the change from one state of matter to another. So solid to liquid, and notice the arrow goes both ways. So we're going to talk about back and forth, and also liquid to gas, and gas to liquid, and there's even solid to gas and gas to solid. So to point out one more thing on this figure that wasn't really around in chapter 1, this is an addition, that from gas to liquid to solid, there's increasing intermolecular forces of attraction, and from solid to liquid to gas, there's increasing kinetic energy. So if kinetic energy is increasing, say, as we go from solid to liquid to gas, then that means that there must be an increase in energy, right? So energy has to be put in somehow in order to go from solid to liquid to gas. So let's take a look at these phase changes, what they're called, and how they relate to energy. And so this is actually quite a nice diagram that I like because of the verticality of it. It's showing us a solid liquid to gas again, and we're seeing the energy increases as we go from solid to liquid to gas. So now it's going up in the vertical axis. So if a solid melts into a liquid, energy was added. If a liquid evaporates into a gas, energy was added. And of course, the opposite, the reverse, would be true. And this matches our experience, right? For a liquid to freeze, you have to remove the energy, right? It gets colder. For a liquid to evaporate, you have to add energy. It increases, its temperature increases its energy, right? So we can see also the back and forth arrows. Solid to liquid, is a melting process. It's called melting, right? But then liquid to solid is the reverse of that. And so freezing and melting occur at the same temperature in similar ways. They're just opposite or reverse processes. A liquid can evaporate or boil into a gas. Gas. And on the flip side, of course, a gas can condense into a liquid if you remove temperature or remove energy. And less common to us, but still possible, is skipping right over the liquid phase and sublimating into a gas. So one example here would be dry ice, which is just solid CO2, and it melts, or you could say sublimates into gas without going through a liquid. That's why it's called dry. Gas to solid is called deposition. Okay, so the question down here at the bottom, is this a physical change or a chemical change? You can think about that for a moment, right? A chemical change is one in which bonds are broken and new bonds are formed, right? The actual identity of the substance changes after the reaction, right? Like water becomes hydrogen and oxygen or something. It's no longer still water. And so here, right, we're talking about, for example, let's say water, like these are phases of water. So throughout these entire processes, we can go back and forth between them all, we still just have water, right? So there is no chemical change occurring. In fact, these are physical changes, right? Melting, freezing, boiling, condensing, these are all physical changes, which have to do not with the bonds within a molecule, but intermolecular forces, right? So how are the, say, molecules of H2O interacting with each other? It's still H2O, but the way that they're interacting can change, right? And that's a physical change. So, like most things that we've talked about, we ultimately think about the energy of what's happening here, right? The energy and intermolecular forces help explain phases as well as phase changes. So in this example, we have a beaker of water on a hot plate, right? So the whole thing is heating up, and eventually it's boiling, right? And boiling just means it's going from the liquid to the gas phase. And if we were to look at the surface, which we have a zoom in here, we see water molecules represented by the dots. So each dot is like a water molecule, H2O. And when they're in the liquid phase, they're kind of moving in all directions, right? There's still random motion. They're fairly close together, but there's some sort of surface, right? And at that surface, a single water molecule may escape the intermolecular forces that it has with the other water molecules around it and move into the gas phase. Of course, gas particles may revert back into the liquid phase. It's like a dynamic equilibrium, right? There's things happening in both directions, but it's all about particles escaping intermolecular forces or being recaptured by them. And why would they do that? Because they have different energies, right? If a particle of water acquires enough energy through the addition of heat energy, it may be moving enough to escape from the intermolecular forces of attraction of the particles around it. Okay, what else is happening during a state of change? a change of state or a phase change. So this is just kind of to repeat that intermolecular forces of attraction are formed or disrupted during a change of state. But again, covalent bonds are not changed, and they are physical changes. So if we're talking about intermolecular forces of attraction, remember that we had this kind of sequence of thinking, right, that went from talking about covalent molecules and their Lewis structure helped us determine their shape, like their molecular shape in 3 dimensions, and then that helped us figure out polarity. Polarity determined intermolecular forces, and now intermolecular forces have something to do with the phase of a substance. So if we think about polarity, polarity highly influences intermolecular forces, which highly influence phase, right? And this is an interesting chart. So let's spend some time on this. We see different substances listed here, and then the boiling point, right? So for example, water has a boiling point of 100 degrees Celsius. So here at room temperature, which is about 20 to 25 degrees Celsius, the temperature is below the boiling point. Boiling point is liquid goes to gas, and so it is still found as a liquid. Right? If you encounter a substance that has a boiling point below room temperature, then that means at room temperature we're above the boiling point in terms of average kinetic energy, and so you'll find it as a gas. And so for all of these substances here that have boiling points below room temperature, they are found as gases in just normal atmosphere, right? And why is that? Look, they're all non-polar molecules. You remember that non-polar only have dispersion forces. And dispersion forces are the weakest intermolecular forces, right? And so the temperature at just standard room conditions is enough to overcome those forces of attraction, and we end up with gases. Here we see some substances that have boiling points above room temperature, so they are liquid, and they are all polar, right? So polar compounds have access to dipole-dipole, as well as some of them have hydrogen bonding. So like for water, for example, right? Water is actually it's a very small molecule, but it has hydrogen bonding. So therefore, it's a fairly high intermolecular forces of attraction, and it's a liquid at room temperature. So the key takeaway is that the type of intermolecular forces affect boiling point, which is, it determines this phase that we'd find at normal conditions. And the stronger intermolecular forces means that there's more attraction between molecules, which means more energy is required to break them apart or move them away from each other. Okay, I'll give one example and then we'll finish this first part. Let's take a look at vaporization. So vaporization is liquid to gas, right? And the energy transferred to the to the substance evaporating, right? Because gases have higher kinetic energy. The energy has to come from somewhere. So it's being absorbed from the surroundings, which means so it increases the kinetic energy of the liquid molecules enough to disrupt the intermolecular forces of attraction, and molecules enter the gas phase, right? So when we think about something like sweating, why does sweating cool you off? because now there's a liquid on your skin, right? And when that evaporates, evaporation requires energy transferred to the liquid. Where does it come from? It comes from your skin, right? And so in the process, your skin actually releases heat energy to evaporate the water of your sweat, which then reduces the temperature and cools off your skin. That's an example of energy transfer. But every phase change involves an energy transfer. Okay, we'll stop this here and hit up part 2 next.